In ideal fluid dynamics, energy is perfectly conserved. As fluid moves along a streamline, it neither gains nor loses energy. This diagram shows that idealized assumption. Notice the total headline at the very top. It remains perfectly flat across the entire pipe length, representing a constant energy state without a single drop in potential. Real fluids have viscosity. When a viscous liquid moves against a physical pipe wall, it generates internal friction. That friction continuously bleeds energy from the system in the form of heat. In reality, the energy grade line slants downward. The gap HL is permanent friction loss. Below it, the hydraulic grade line charts only the piezometric head, static pressure plus elevation. The strict rule, it sits exactly one velocity head below the energy line. While the energy line must strictly decrease in the direction of flow due to friction, the pressure does not have to follow. If the pipe geometry expands, the fluid velocity drops. The system exchanges that lost kinetic energy for static pressure, allowing the hydraulic grade line to physically rise even as the total energy falls. Differentiating between total energy loss and physical pressure fluctuations is the basis for analyzing real-world infrastructure. We calculate that continuous downward slope of the energy grade line using two specific mathematical engines. This cross-section illustrates the variables for longitudinal surface friction. We determine this major loss using either the Darcy-Weisbach equation or Chezy's formula. To convert between these methods, the bridge equation is Chezy's constant c equals the square root of 8 times gravity divided by F. Keep your variables precise here, that F represents the Darcy friction factor. Do not confuse it with the friction coefficient, F prime. The friction factor is exactly 4 times the friction coefficient. Surface friction only accounts for straight stretches of pipe. Real networks are filled with physical interruptions, closed valves, sharp bends, and sudden expansions. Every one of these obstacles forces the fluid to separate and eddy, causing highly concentrated drops in energy. We define these geometric interruptions as minor losses, calculated by multiplying a component-specific coefficient, K, by the fluid's velocity head. Calculating total system attrition is a process of addition. You tally the continuous tax of surface friction along the length of the pipe and add the sudden tolls taken by every geometric obstacle along the path. Once you move beyond a single pipe, you face sprawling matrices of interconnected infrastructure. Solving these requires an overarching logic system. This split screen visualizes the most reliable method for mapping complex networks, the electrical circuit analogy. The mathematical structures are identical. Fluid discharge, or Q, acts as the electrical current moving through the wires. Frictional head loss acts as the voltage drop across a resistor. We apply this analogy to two distinct configurations, starting with the series network. Look at this diagram detailing a series configuration. When pipes are arranged strictly end-to-end, mass conservation dictates that the total discharge Q is perfectly constant throughout the entire system. The energy penalty, however, stacks. The total head loss is strictly cumulative across all sections. A critical diagnostic shortcut for these configurations relies on the continuity equation. Velocity varies inversely with the square of the pipe diameter. That means the narrowest pipe section will always force the highest fluid velocity, driving the steepest drop in the hydraulic grade line. However, parallel networks flip this logic entirely. When a pipe splits into multiple parallel branches, the head loss is strictly constant across every path because all branches originate and terminate at the exact same energy nodes. Consequently, it is the discharge that becomes cumulative, with the total flow equating to the sum of the individual branches. To simplify analysis, engineers collapse these complex branching matrices into a single mathematically identical equivalent pipe that generates the exact same head loss for a given discharge. This matrix isolates the specific tool to execute that system collapse. The Dupuy equivalent equates the length over diameter to the 5th power of the equivalent pipe, to the sum of those ratios for the individual pipes. By treating pipes like electrical resistors, you can mathematically reduce a seemingly impossible maze of infrastructure into a single, predictable fluid pathway. Every single pipe system is ultimately bounded by hard physical and mathematical limits that no amount of engineering can bypass. Consider the siphon. It transmits fluid over an obstacle higher than the source reservoir by utilizing subatmospheric pressure at the highest point of the pipe. The absolute theoretical limit of this lift is dictated by atmospheric pressure. Water will vaporize completely at absolute zero pressure, capping the maximum theoretical siphon lift at roughly 10.3 meters. In real-world operation, dissolved gases and the severe risk of cavitation restrict this limit further. The maximum functional siphon height for water is strictly 7.8 meters. Any design calling for a 9-meter siphon is physically impossible. Beyond elevation, we encounter strict energy utilization boundaries, specifically regarding power transmission through a pipeline. Look at the efficiency equation for power transmission in the bottom left. Efficiency is simply the ratio of the physical head available at the outlet versus the total gross head supplied at the inlet. When you differentiate this power equation with respect to velocity, you hit a hard mathematical wall. Maximum power is achieved only when friction loss consumes exactly 1/3 of the total available head. Because you must sacrifice 1/3 of your energy to friction to hit peak power delivery, the maximum possible efficiency is permanently capped at 66.67%. Recognizing these hard operational boundaries, a 7.8-meter siphon lift and a 66.67% power efficiency limit, allows for the immediate identification of impossible design scenarios. Everything discussed so far applies strictly to steady-state flow, but those rules disintegrate the moment a system experiences a rapid operational change. This animation shows a high-velocity fluid column. When it collides with an instantaneously closed valve, the fluid doesn't simply stop, it compresses. We define this event as water hammer. The steady fluid momentum is instantly destroyed and converted entirely into a massive, backwards-traveling acoustic pressure wave. This rule matrix highlights a crucial directive. If you see the phrase sudden closure, standard friction physics no longer apply. You calculate this transient surge using shockwave equations. For a rigid pipe, the pressure spike P equals the fluid density multiplied by the speed of sound within the fluid, multiplied by the velocity that was destroyed. Understanding system transients separates theoretical textbook calculations from predicting and preventing catastrophic explosive pipe failures. Mastering fluid mechanics for the APPSC AEE exam requires the ability to instantly identify which specific fluid regime a prompt is targeting. Examine Figure 7.11 here. When presented with a complex multi-junction network like this, your first diagnostic step is to map the continuity and mass conservation logic. The logic is straightforward. The total discharge approaching the junction must equal the sum of the flows leaving it. By substituting the given area and velocity data into the total discharge equation, you easily isolate the missing velocity for branch 2, yielding exactly 5 centimeters per second. Next, check for absolute boundaries in the question data. Look for the 66.67% power efficiency cap, or the 7.8-meter siphon limit, to immediately eliminate impossible multiple-choice answers without touching a calculator. If a problem mentions sudden closure, calculations must shift to shockwave equations, as standard Bernoulli concepts do not apply in these transient states. This architecture of energy, friction, and momentum allows for the systematic modeling of real fluid behavior across any pipe network.